Hello everyone, it's March 25th. Alright, let's do this. In and out, in and out, in and out. Minimum operation to make unit value grid 2D integer grid of size n by n of integer an integer x. In one operation, you can add x to or subtract x from any element in the grid. A unique value grid is the grid where all the elements are equal. And turn a minimum number of operations to make the grid unit value. Well, if it's a 1, it always will work. Ah. And I think the last one will be -1. Yeah, 2 doesn't work. And the minimum number of times, right? Where you use. Oh, yeah. So, I think it's just dressed up as this, but essentially it's an array, right? It's an array, and then you have an x equals 2, and you say, can we make this converge it into 1? Well, I think, can you prove that it's always something in the middle, right? We want to do something in the middle. If we do something in the middle, or we can, because it's just the number of steps, right? The number of steps. What's the minimum number of steps? There'll always be a target number, right? So we have a target number, and then some will be bigger, some will be smaller, right? So we can actually go the other way around. Right? We can actually go the other way around. Can we prove that it has to be one of the member? Right? We can say if it's not one of the number, so we can pick someone, right? It's not one of the number. And then we say that one will yield a better thing, right? So that one will yield a better result. Yeah, I would say it will be something in the middle, but I don't know how to prove it. Well, actually, if it's this, right, and then we say we have a target called y, called t, right? So t will be somewhere. So it's just gonna be, t minus, and if I say this is a0, a1 all the way to an divided by 2 plus t minus a2, a1 divided by 2. So we don't have to even worry about this. We just add them together, right? If we add them together. And what we want is for this value to be minimal. Now, for this to be minimum, if let's say t is really big, right? If t is really big, then it's basically n times t minus a0, a1, right? All the way to an. If t is a big value. Now, as we move, so the other extreme will be a0, a1 minus n times t, right? This is the other extreme. Now, this is a non-value. The bigger the n, the bigger the t, then the worse it gets, right? So now we all come to a position where we're kind of inside. So we'll have, let's say, t minus a0 plus t minus a1, right? Let's say t minus am, and then am plus 1 minus t, am plus 2 minus t, all the way to an minus t. So in this case, we'll have basically, well, if we want to say m, so let's do n minus 1, and this will be am. So we have m times t minus a0 all the way to am minus 1 plus am plus an minus, basically this, how many? N minus m plus 1 times t, right? Now, because we are sorted, so every single value here is bigger than that. And we can expand this, so this is m times t minus nt plus mt minus t. So that's 2, really? Yeah, that will be 2mt, 2m minus n minus 1 times t plus am an minus a0 am minus 1. That'll be this. So what we can do is go through every single one, put it into this formula, and see what we got. Right? But it also has to be divisible by this. It has to be divisible. But you also need to make sure that it's all divisible. How do I make sure it's divisible? Oh, I just realized. Hold on. Let me redo this. A1, A2, all the way to AN. Right, and then I say among these has an AM in between. Right, has an AM in between. And then I say our target is in between this, AM minus 1. So, right, so it's going to be T minus A1 and every single one has to be divisible. Right, so this is M times T minus A1 plus 2AM plus AM plus 1 AN minus N minus MT. Right, so it's MT minus N plus M, so 2M. 2M minus N T plus AM plus 1 AN minus A1 AM. Right? So if we sort it like this, I can decide where M is. Right? I can pick any M, and when I pick the M, because I pick M, I know M plus 1, so I know what the T is going to be. T t is just somewhere in between, right? T is somewhere in between. And I have this value. And I also have this value. This can be acquired from prefix sum, right? So as I go through, because n is determined, I just go through m, right? I can set m to be here. Like it cannot be outside, right? Because if it's outside, I always have a better solution. So I can pick m, like I can say m equal to 1. Right? I can say m equal to 1. So just the first one, right? And then it will just be, minus a1 plus a2 to the end. So I got that. So this t can be anywhere in between, right? Anywhere in between this. Now this is also deterministic, right? This part is also deterministic. Once I get the m settled, this one's deterministic, and I can't just take a1 as well. And if I take a1, so this is just essentially yeah, it doesn't matter because this, like, I can take t to be a1, right? If t is a1, then we'll have 2 minus n times a1 plus a2 to an minus a1, right? So, and then and then this is a1 minus n times a1 plus this, right? And then this n minus 1, right? So this is basically, we say it's a2 to an minus n minus 1 a1, right? And then would this disappear? Yeah. Yep. So yeah, decide on what do we pick on the t. So for each m, right? For each m, I have a couple of t to choose from. And given that we are talking about 10 to the 4, okay, 10 to the 4, so it's not that big. So I can just, I was wondering if maybe we can brute force this, or I don't know. Okay, we have this formula. Next, we need to prove. If we can prove it has to be landing on one of the numbers, right? It has to be one of the numbers. Well, if it has to be one of the numbers, would it be like not a number, right? Because it's landing in between. Well, can we have some proof? Let's say 2, 6. Right, we can actually add a little bit more. Say 0, 2, 6, 8. Apparently, if we pick 4, then this difference is 2. This is 4 plus 2 plus 2 plus 4, right? If I pick any of this, like I pick this, that will be 2 plus 4 plus 6. Oh, this is a probably not a good example. What if I pick 5? Good question. If I pick 5, that'd be 5 plus 3 plus 1 plus 3. Huh. Are you telling me it's the same? I think. Wait a second. 2, 4, 6, 8. So if I pick 2, it's gonna be 2 plus 4 plus 6. The difference. That's 12. I pick 4. So 2 plus 2 plus 4. Nah, that's 8. Right? There is a difference. I think it's within this range. It's the same. Hold on. If I pick 6, if I pick 2, if I pick 4, if I pick 6, that's 4 plus 2 plus 2. That's 8. If I pick 8, that'd be 6 plus 4 plus 2. It's 12. Alright, so what if I pick 3 in between? That'd be 1 plus 1 plus 3 plus 5. What's this? Ha! It's 10. What if I pick 5? 3 plus 1 plus 1 plus 3. That is 8. What is the pattern here? And of course, if I pick 7, that's 1, 5 plus 3 plus 1 plus 1. Yeah. That is 10 as well. So I'd say it is going, but how do I prove it? How do I prove that? Because I know on the most outside it is worse, right? Because everybody has someone. Then I come here. And as I move, right? As I move, I wonder if this one can give me some hints. Right, as I move, as the t moves in this range, so a t will go big. Right, t essentially starts at I say the extreme is t equal to 0, right? T equal to 0 is the extreme. And if you have t equal to 0, then it's just, a1 plus a2, which is the entire thing. That's the maximum you can get. Well, I mean, yeah, right? And then as t moves, before it can hit, as the t gets bigger, right? In this case, yeah, in this case, m is 0, right? M is 0, so this is the whole thing minus nt. So the bigger the t gets, the smaller, right? It gets smaller. Okay. And then you hit Yes, yes. Essentially, as t, like when we settle down on the m, right? We settled on the m, then everything is static, right? If I know m, then the bigger the t gets. So depending on 2 times m and n, if 2 times m is smaller than n, then 2m minus n is a negative value, right? It's a negative value. Once it's a negative value, because we will plus something, right? Plus something, it doesn't matter. So we'll get smaller if t gets bigger, right? If t gets bigger. So if we move towards the right and m gets big, right? If m gets big, okay, if m gets big, then the right hand side is a negative value. Then the bigger the t gets, also the bigger the thing gets. So we don't want t to be big, right? If m cross the halfway point, we don't want t to be big. Yeah, if m cross halfway point, right? If m cross the halfway point, the bigger the t gets, the worse. But if you get through the halfway point, we also have, I mean, essentially, if we pick an m, right? If we pick an m, if it's on the right hand side, like if 2m is larger than n, right? If we pick an m, we say, okay, we'll do this one, right? We'll do this one, and the t will be in between this and the it'll be here. Then you should get the t as small as possible, because the bigger the t, then the more positive it becomes, right? So we should settle on the actual value itself. Now, if you're on the left hand side, right? If you're on the left hand side, then you want the t to be as big as possible, right? Because the bigger the t gets, then the more negative you get on the left hand side, which means you get the whole thing smaller. So you want to lean to the right as possible, so you also land on the value. So yes, this is my proof. I can prove it that the optimal value should be landing on one of them, on the actual number itself, right? Okay, so now we have this, so we know we just need to go through every single one. So now we have this one, then what, right? Then what? I have basically, I know the sum, right? It's just like, if we have to be like landing on one of them, it's fine, right? It's totally fine. We can have everything towards the left, right? Basically this minus this minus this minus this, and everything on the right, right? Everything on the right, and yeah, we can definitely do this using the same, actually, same thing. It's just t will be, you know, because we're saying the am, right? Oh, that doesn't, so we're setting AM, and then we have a minus 1. We need a value. It's okay. We can just always use on the towards the left. It's alright. It's alright. We just say we set this one, right? When t is equal to this one, and yeah, we can use this to handle every single one. And once we go through this, we will find the minimum, right? But now the question is, how do we make sure that like it's divisible, right? So it's like every difference has to be divisible. So we have a difference, right? Difference, and difference, and their difference must all be divisible by x. If one of them is not, then it's not. Now, if this is divisible, I'm trying to think, because as I move forward, right? So if like I have this, if this is divisible, and this is divisible, all right? Then we can say the difference between those two is also divisible, right? The difference between those two is divisible. And if the difference between those two is divisible, can we say we put another value in there that they will still be divisible? I don't think so, right? I don't think so, because this minus this is divisible doesn't mean I can do this minus this, minus this, right? I can do that. It's divisible. But every one by themselves is not necessarily divisible, because, you know, odd minus odd can become even. Then how do I quickly check that given a single value, it is good? How do I check? Because 1, 2, 3, 4, right? You can set it to be 2 or 3. I think you will give the good. Like if you do 1 is 1, 2, 3, 6. If you do 2 is 1, 1, 1, 1, 2. Right, it's 4. You do 3 is also 1, 1, 2 is 4. You do 4 is 6. So I have 6, 4, 4, 6. So we know the answer should be, you know, either 2 or 3, right? But if it's 2, we'll find that we cannot do x. So how do we get this one fast? Like given everyone, I have to check all of them. I don't think that's possible. How can you check for everyone? Or you start from something and you check for everyone. So like I start from 1, right? So I got 1. I got 1, 2, 3. Okay, and it's not good. Now move to the next one. So all the deltas, right? All the deltas gets changed. But you have to monitor all the deltas? How is it possible? You have to monitor all the deltas. Okay, so if it is not possible, if it is not possible, well, can we say if one of them is not possible, then the entire thing is not possible? Can we say that? Well, I don't know. If one of them is not possible, which just means I have a difference which is not divisible by x. Okay, let's say we have something not divisible, and then we say another one is possible. Right, that means this minus this is good. So what I'm trying to say is if I have a AP and we have an AQ, right? Now we have an AX. So we say it's not possible because AX minus AP is not equal to KX. So it's not divisible. Okay. And for the sake of complex, I can say AX and AQ is, okay. So now I say I have an AY, right? And we say it's possible for AY to work. So AY minus AP equal to KX, right? Equal to something X, right? And AY minus AQ is also equal to something X, right? And AY minus AX is equal to something X, right? That's very important because that means AY is a possible case. So what we want to prove is by doing this, we'll have, because we need to prove that this is not possible because AX is not. Okay, so we have this, and we pick these two, we do this minus this, so we have AX minus AP equal to something X, but our start hypothesis is this is, so that's contradictory, which means as long as you find one of them, right, one of them doesn't work, then the whole thing doesn't work. Okay, one of them doesn't work and the whole thing doesn't work. That is, so can we say on the other hand, if one of them works, then the whole thing works? Is that also right? Yeah, if one of them works, right? So let's say AY works. So I say AY minus A1 is good. AY minus A2 is good. Now an plus 1 minus ay is good. Right, all the way to an minus ay is good. They are all good. Right? So they are all good. So if I want to pick, now it's ay, let's just call it am. Right, we'll do am. Yeah, we'll do am. So this is all good. Now we want to find another one. Let's say, AP, right? It's also in this. Now I want to find out what is AP minus A1. Now I have AM minus A1 is good. And I have, well, if I have AM minus AP is good, then they will be good. If I have AP minus AM is good, then you add them together, this is also good. So yes, once one of them is good, everybody is good. Okay, so we have proved two things. First, the minimum will definitely happen when we land on one of the values, right? That's the first thing. So we only need to check these. The second is if one of them works, then everybody works. And if one of them fails, everybody fails. So with these in mind, we can just do two things. First, to check if it's possible, I can just use, this doesn't matter. I'll get all the value out. I will order them, sort it, and I just pick the first one and I run through the sequence and see if it works. Well, we'll get the prefix sum, right? I think getting the prefix sum is important because I have A1, A2, all the way to AN, right? If I get a prefix sum of this, because remember, if I get an AM, right? So basically it's going to be AM minus A1 plus AM minus A2, right? Plus 2AM minus AM minus 1. And then it's AM plus 1 minus AM. Right, AM plus 2 minus AM, and all the way to AN minus AM. So this comes down to n minus 1 times AM minus A1, A2, all the way to AM minus 1 plus AM minus 1, AM minus 2, plus 1, my bad, plus 1, plus 2, all the way to AN minus, this is N minus M times AM. That's not right. No, that is right. That is right. Because, yeah, that is right, right? So this is that. And now we combine these two, which will get, so M minus 1 minus N plus M. So it's 2M minus N minus 1, right? Times AM minus, so if I have an S, right? S1, S2, Sn, this is a prefix sum, then this is Sm minus 1, and I will plus, this is Sn minus Sm. Right? So this is the kind of the formula. So I can just go through the whole thing one by one and plug the number in. Right? Plug the number in. And of course, in reality, I have, because this is from 1 to n, right? But the index is going to be 0 to n minus 1. I'm not sure if it's going to cause any trouble because these are the counts, right? These are the counts. We can do, I think it's fine. I think that's fine. We shall be able to do the conversion. Yeah, so we can do that. and we just find the smallest. Okay, let's give this a shot. Let's see if the proof works. I think I took a lot of time just to make sure we are happy with the proof. I don't think I'm gonna give the proof a little bit more detail. And so, okay, let's do this. I think I can prove, right? That's essentially what it is right now. I think I can prove it, right? Now I think I can prove two things. First, the minimum. No, hold on. This is also there's a one more thing, right? To find the min operations is equivalent to find the sum, right? The sum of all the deltas, right? Of all the absolute deltas, right? Absolute deltas. Based on this, right? Based on this, I think I can prove two things. First, the min total sum, the min sum of deltas is achieved when the convergent number is a member of the grid. And two, if one of the grid member, right, can make it happen, any member of the grid can make it happen. And if one of the grid member fails, then if one of them fails, then no other member can succeed. That's kind of the two insights I think I can prove, right? So based on this, I'm gonna write O and log n. So here is my insight for this. So to begin with, we need a vector of, we can say this is the p sum, right? P sum will be, so we have m, n, right? So p sum can be m times n. So I need a p sum, and I also need flatten. Right, so this smaller than m. All right, so I can do both. Flatten, what's this value? I believe it's I times n plus j. Right, so this is gonna be, honestly, it doesn't really matter that much if you think about it. Right, it doesn't matter that much. But it's okay. So yeah, so I did this to grid ij. Oh, we do have a situation of, so maybe it is easier to, because like in this case, if m equal to 1, then I have an S0, which you don't have S0, so we probably should have an S0 here. Right? We probably should have an S0. Oh. Alright, now we say p sum I times n plus j. We probably, let's call it index. Alright, so this is that. And now we need to do so given an array. Oh, we need to sort it. Oh, we can't even do it right here. Damn it. Because we need to sort. Ah, shoot. Do we need to sort? I don't think we need to sort. Like, this one doesn't imply any order. So, we know. I think we don't have to sort. A1, A2, A3, AN. Right. If we choose AM to be the convergent, number, and prefix sum, and prefix sum array S0, S1, Sn. If we choose M to be the convergent number, the total sum is a sum we want to minimize. Minimize is 2 times m minus n minus 1 times am, right, minus s m minus 1 plus Sn minus Sm. Alright, so with this, I got a flattened, I got a p sum, which is completely fine. Then what? Then I need to first check to see if it's possible, right? So we're gonna check to see, right? Check if it's possible. Check if possible. So I use flatten 0, right? So we can say for I the y smaller than m plus n I plus plus if flatten I minus flatten 0, right, mod x is not equal to 0, so we have an impossible case. And once we find one impossible case, then we can find all the other impossible cases. So if it's impossible, then we return -1 immediately. Right, return -1 immediately. Alright. And then next is find the smallest. Sum of delta. So min sum delta, which I'm not sure, and it probably will go beyond though. 10 to the 4th times 10 to the 5th, 10 to the 9th. Oh, I guess it won't go beyond. Okay, we say for int I 0 I smaller than m I plus plus. So int current sum, current shall equal to this 2 times. All right, I want maybe it's, I don't know, what do you think? T. Okay. All right, T. So 2 times m is a count, so it's actually going to be I plus 1 minus, this is the total, minus 1 times flatten I minus p sum. Now this is going to be, is it just whatever I'm pointing at when we go to the previous one? So we can do essentially is I plus 1 is reflecting on there, so I plus 1 minus 1, so we're going to do p sum I plus p sum, that's the last one, so it's going to be t minus p sum. That's m, so that shall actually be I plus 1. So we do this, that is that, and oh. Huh. If it is possible. Then we say min, minimum. So at the end, you return alright, let's give this a shot. I went out of bound. Okay. How? I don't know how, but apparently that's how we got it. The second one basically I do should be 1, 5, 2, 3. Oh, I think sort is important. Yeah, I think sort is important. So in that case, I'll flatten it first. Right, I'll flatten it. Don't do this, so I'll flatten it first. I'll sort flatten dot begin, flatten dot end.
Oh.
And then we say for. P sum I plus 1. So you go to P sum I plus flatten I. So now we have sorting included. Let's try to see if it make a difference. Let's give it a shot. Yep, we got it. So aggressive analysis, and we finally got it. One shot, which is not bad, but dude, this is a little bit frustrating because it took about an hour. Sorting and a medium. Yeah, you can directly go to medium. Oh, I think you can directly check. Yeah, you have to prove that it is in the middle. I think I just couldn't prove it that it has in the middle. Yes. Why the medium is a balancing point? Yeah, there gotta be a formal proof for this. We have a proof. We have a proof that actually we can see it from here. We have a proof. Like when we go big, then we want to lean towards the left, right? And when we go small, we want to lean that. But I think there's a formal proof here. Yeah, I think it's here. This is the thing that we want, right? We say if this is kind of small, if it is smaller than n, then we want this one to be big. If this is bigger, then we want this one to be small. So we shall find the medium. Medium will give us the best. Okay. Yeah, we grasped the gist, but I guess it's just not bold enough. I was not bold enough to go right for the medium. But yeah, anyway.